This video is part 3 of a 3-part video series on Air-Fuel Alliance magnetic charging measurements using a scope based on magnetic resonance, which operates at 6.78 megahertz. Now this particular video, part 3, is focused on making power and efficiency measurements, PTU to PRU, sometimes called resonant coupling efficiency or RCE. Now frankly, these measurements are not included in the conformance test specification. Determining efficiency in this type of system is usually done with a network analyzer based on S parameters and impedance measurements. And in fact, Keysight has network analyzers with the built-in option for automatically determining efficiency based on various parameters. But what I've learned from talking to engineers that are designing these systems, once they get a system up and running, they definitely want to use a scope as more as a reality check to determine what is the power quality of both their PTU and PRU, as well as determine what the efficiency is, so they can then make tweaks and then make improvements. Now the most important thing you need to do when making either power or efficiency measurements is you must first de-skew your probes. You're typically using, or you should be using, a differential active voltage probe as well as a current probe in order to measure power. Now there can be a delay difference between the voltage probe and the current probe, and that must be de-skewed. Keysight offers a de-skew board where you can automatically de-skew your probes, but I have something better. It's simply a 10 ohm resistor. The scope actually has a built-in waveform generator, and we can produce a 6.78 megahertz sine wave and calibrate it based on that signal. And this simple, inexpensive 10 ohm resistor actually does a better job than the de-skew board. Let's de-skew our probes now. First thing I'm going to do is connect the probe up to the output, not the probe, I mean my de-skew fixture, my 10 ohm resistor, to the output of the generator. I already have my generator set up for a sine wave at 6.78 megahertz and the maximum output swing, which is in this case 10 volts peak to peak. Next, I'll connect my current probe around the resistor and then connect the voltage probe across the resistor. The scope, if it has a built-in power app, that's an option on the scope, go into the Analyze menu, select Power Application, and then we have a list of measurements that can be performed automatically. Now this was optimized for switch mode power supplies, but we can use it on magnetic resonant charging signals. I'll select Power Quality, go into the Signals menu. Here we show a diagram of a switch mode power supply. You could ignore that. Assign my voltage probe as channel 1, current probe is channel 2, and over here it says de-skew. This is where I can do the automatic de-skew. Here it shows a block diagram of the de-skew board. Again, I'll ignore that since I'm using my 10 ohm resistor, and then just press auto de-skew. It'll automatically optimize vertical scaling of both the current waveform, the voltage waveform, and then perfectly align the signals. In this case, we're measuring a skew of 5.48 nanoseconds. Now, if we didn't perform that measurement, or this de-skew, we would get significant error, and I'll show that later when we begin to make efficiency measurements. I'll pull that de-skew calibration back out, and you'll see the difference. So let's get started making power quality measurements. We're going to begin with a power quality measurement on the PTU, or the transmitting coils. Begin by connecting your current probe to the PTU coils, as well as the differential voltage probe across them. Let's begin. I'll select what's called the Analyze menu, and then go into the Power Application. These are all the automatic power type measurements we can perform. This was optimized for switch mode power supplies, but there's a few of them we can use on magnetic charging. We're going to select the power quality, go into the Signals menu. Here we can assign which channel is the voltage. In this case, we can use the default channel 1. Current is channel 2. The default number of cycles it performs the measurement across is 2 in this case, which is not good for what we're doing. Let's select about 20 cycles to perform the measurement across, and then simply press Auto Setup. This will optimize the scaling of both the voltage and current waveform and turn on the power waveform, which is the instantaneous voltage times current, and that is the purple waveform. Then I'll press apply, and here we see automatically all our power measurements. Power factor, real power, this is the one you're probably most interested in. Apparent power, reactive power, crest factor of voltage, crest factor of current, phase angle, in this case it's about 33 degrees. It turns on a DC RMS, you may not care about that one, and frequency. Now we can add to it a counter measurement that will give us a more accurate measurement of the frequency. Let's do it on the current channel. Move that over to the side. So there we have 5-digit frequency measurement, and we may want to add a current measurement. RMS current measurement. Select AC RMS in cycles, and there you can see we're measuring about 516, 517 milliamps. Now if we want to perform the same measurement on the PRU, again we can go back into that menu, and in this case I have my channel 3 and channel 4 connected up to the PRU. Select 3 for voltage, 4 for current, auto setup. Then apply, and there we have the power on the PRU. And probably the last measurement, and maybe the most important one, is the efficiency measurement. So let's select efficiency, AC to AC, go into the signals menu, redefine my input voltage as channel 1, input current is channel 2, output voltage channel 3, output current channel 4, duration 100 milliseconds. Again, this was optimized for a switch mode power supply. I'm going to change that to about 4 microseconds. That's the time span that we'll be making the measurement across. Then press auto setup. This auto setup takes a little longer. It's got to optimize 4 input channels: input voltage, input current, output voltage, and output current, and then turn on 2 different power waveforms, one for the PTU and one for the PRU. Then we'll select apply. There you can see our input power, output power, and efficiency. Now you may notice the input power is lower than what we were measuring when we did the PTU power quality measurement. That's because, again, this measurement was optimized for switch mode power supplies. It automatically turns on bandwidth limit on all channels, so we need to turn that off, and we'll probably see it bump back up to where we saw it before. And so we're measuring about 70% efficiency. Now if you zoom in, you'll see I'm using an arbitrary waveform generator. I've added some noise to the signal to make it a little more realistic. If you want to make it more stable, you can turn on waveform averaging. Let's do that. Crank it up to maybe about 32. Now we can get a more stable measurement. Remember, we de-skewed the channel 1 and channel 2 voltage and current probes, and there was a de-skew factor of 5.48 nanoseconds. I'm going to remove that now. So remember, we're measuring, it says about 69%. I'm going to go into the channel 2 menu, which is where the de-skew factor is, and I'm going to plug in 0 nanoseconds. Notice it jumped up to 84%. So if you don't de-skew your probes, you're not going to get accurate measurements. Well, thanks for watching this video on making power and efficiency measurements in a magnetic resonance system based on the Air-Fuel Alliance standard. We have 2 other videos. If you haven't watched them, I encourage you to go watch those. The part 2, especially on beacon timing, current and frequency measurements. We also have 3 application notes that go right along with these 3 videos. You can download them at the URL listed on your screen, and I thank you for watching this video.